Hello, Heritage Academy Geometry students, and welcome to Geometry, Seeing, Doing, Understanding, Lesson 2.6, Set 1 Guide. I'm going to take you through some selected problems in Set 1 today so that you're feeling a little bit more confident about some of these theorems that were introduced in the lesson. So for these selected problems, I'm going to start us at number 11 at the top of page 68. And when you open up to your book there, you're going to see this picture. And it says this target figure consists of 5 circles with radii of 1, 2, 3, 4, and 5 units. Number 11 asks, what are the diameters of the 5 circles? So remember that your diameter is twice the distance of your radius. So if your radius is 1, your diameter is 2. Very good. So this means that for number 11, we would end up with diameters of 2, 4, 6, 8, and 10 units because we're just doubling each of the radius measurements that we were given. For number 12, it asks what are the exact circumferences of the 5 circles. So now we need to work a little bit with our circumference equation. And remember that our circumference is where we take our diameter and we multiply it times pi. So for number 12, for our purposes here, you can just leave your answers just like you see here, 2 pi, 4 pi, 6 pi, 8 pi, and 10 pi. You really don't need to simplify them any more than that. For number 13, it asks what is the exact area of the purple region. Now here's where we have to dig a little bit and pay a little closer attention. So notice that our radius is going to be 3 for the purple region. And if we want to work our area equation, we want that radius measurement to help us. So area is going to be pi times radius squared. So when we put that all together, we have something that looks like this. Area equals 9 pi, which if you wanted to simplify that, you could say that it's about 28 units, but we could also leave it at 9 pi for now. Number 14 gets into something a little bit different, which I really like this one because now we have to really think about it. But notice our arrow. This helps us to look at these 2 different regions where we have yellow and then we have the rest of the concentric circles. And this is an important thing because 14 says what is the exact area of the yellow region. So when we look at this, we need to find the area not just of the whole set of concentric circles, but then we need to find the area of that next set in and subtract it from our total that we found for the whole set of 5. And to do that, we're going to go ahead and take pi 5 squared, which would give us that area for the entire set of concentric circles, including the yellow. And we're going to subtract it from pi 4 squared, which is going to take out the rest of the concentric circles that are not yellow. And that is going to leave us with 9 pi, which is actually the same answer we had in 13. So if you wanted to simplify that further, you would again end up with an answer pretty close to 28 units squared. And finally, number 15 asks, why do you suppose that this figure sometimes appears in books on optical illusions? And the answer for this might vary a little bit from student to student, but generally the idea here is that although the purple region looks a lot larger than the yellow region, what we actually have just discovered here by solving 13 and 14 is that they have the exact same area. So 16 and 17 are going to bring us back to the Pythagorean theorem. And it says in your book, in each of the following figures, squares have been drawn on the sides of a right triangle. Given the 2 areas shown in each figure, find the third area and show your methods. So this brings us back to that idea of a squared plus b squared equals c squared. Now remember that c squared is your hypotenuse length. So this is really important because you need to put the right numbers in the right places to make this equation work. So for 16, we have 36 and 64 and some mystery square. Now, you'll recall from when we first studied the Pythagorean theorem that those two smaller squares equal the amount in the larger square when we're talking about the areas. So for 16, we can simply add them. 36 plus 64 equals 100, and 100 is going to be that missing square. However, we can extend the thinking here even beyond what the book is asking us, and we can think, well, if 100 is the missing square, then if I take the square root of 100, I get 10, and 10 is going to be the length of my hypotenuse. So these are things to just keep thinking about in your mind because they're going to be helpful for you as we continue our study in geometry. Now 17 is a little bit different because notice where your right angle is. And remember that the two legs that are not the hypotenuse are going to be connected with that right angle. So what we've actually been given here in number 17 is our c squared, which is 169. And then we have one leg measuring 25 and another leg of which we don't know. So to set this one up to solve, we actually want to take that hypotenuse and subtract the leg that we have, which results in 144. And again, we can take the square root of 144 and we find that we have 12 for the length of that side. One other important thing to recall if you watched the instructor video is that these types of Pythagorean theorem examples are something called Pythagorean triples. And I kind of gave you that name but haven't told you much about it yet. So keep that in mind because it'll be important later on in the learning. Next, we're going to take a look at numbers 18 through 23 on page 68. And we start with when a bird is gliding, its wings produce a lifting force that makes a 90-degree angle with the direction of the airflow at the leading edge of the wing. 18 asks us to look at this image and find angle A if angle J equals 60 degrees. So all we need to do here is remember our theorem that those three angles in a triangle need to equal 180 degrees. And remember that theorem is called the triangle angle sum theorem. And if you did the math, you're going to find pretty quickly that angle A will be 30 degrees if angle Y is 90 and J is 60. So then similarly on 19, it says find angle A if angle J equals 45. So 90 plus 45 is going to give us 135, which leaves us with 45 degrees left. On 20, it asks us to extend our thinking a little bit, and it gives us a variable for angle J. So you've got angle Y, but it gives us n for angle J and says find angle A in terms of n. So you want to set up a little bit of an equation here that looks like 9 minus n. Numbers 21 through 23 deal with this graphic on the right, and it says this figure shows an overhead view of someone at C listening to stereo speakers at A and B. For the sound to be balanced, angle A equals angle B. Now that little piece of information is really important because angle A and angle B being the same number is going to make finding these angles a lot easier. So 21 says find angle A if angle C equals 40. Well, to do this, we can just take 180, subtract 40 from it, and then divide what's left by 2. And the reason we divide it by 2 is because A and B have to be equal. We have to split the difference evenly. And that's going to give us a final answer of 70. And you can see on 21 there that I've put this into a little bit of an equation for you because I want you to be thinking algebraically while we're working through these problems. It's important for future lessons. 22 is going to be pretty similar. Find angle A if angle C equals 50 degrees. So again, we can take 180, we'll subtract 50 from it this time, and then divide by 2 to find that those angles are going to be 65 degrees. 23 now asks us to set this up looking a little bit more algebraic by saying find angle A in terms of n if angle C equals n degrees. So since we've already been writing it algebraically to solve, then the benefit in that is all you need to do is plug n in for that variable number. So the last two problems deal with this triangle, and the book starts us off with this statement. If this figure is a right triangle with hypotenuse C, then a squared plus b squared equals c squared. Now this looks like a pretty well-formed conditional statement, and notice that in number 24, they take our conclusion and they switch it with the hypothesis, and they say, given that this statement is true, does it necessarily follow that if a squared plus b squared equals c squared, then this figure is a right triangle? Now, they've made it into a converse, and although it seems like it's true, the answer might surprise you when you find out it's no. But when we look at 25, here's the reasoning. This is the converse of the Pythagorean theorem, and the converse of a true statement isn't necessarily true. So remember that sometimes we need to develop a few more conditional statements or a few more ideas here to be able to really determine what's true versus what's just sound and valid. There's a difference there between those two things. So we're going to continue to explore these ideas and so much more as we go through this book. But for now, I hope that going through some of these select problems in set 1 helped you to get some good practice with these theorems in geometry. I will see you next time.